Hello everyone and welcome to my talk. My name is Matthieu Simeoni and I'm a postdoctoral researcher at EPFL. Today I'm going to discuss a spherical approximation framework for the creation of an Earth digital twin. So one way to tackle the current environmental crisis is to build an Earth digital twin, or an exhaustive computer simulation of our planet, allowing us to better assess its current and future health, as well as evaluate the efficiency of environmental policies, or finally provide data-driven answers to rising public concerns about environmental and health issues. In order to make this vision a reality, we are going to need an integrated data coming from very different sources and hence highly heterogeneous. For example, administrative data has pretty good temporal coverage, but has poor temporal resolution and accuracy. In situ measurements, on the other hand, have very good spatial resolution and accuracy, but have poor spatial coverage because some parts of the globe are obviously much harder to sense than others. Remote sensing, finally, has good spatial coverage and availability, but is much less accurate than in situ measurements. So if we want to integrate all this data in a common product, we must homogenize it. This means that we must correct as much as possible for sensing inaccuracies, as well as suppress acquisition artifacts that may disrupt the analysis. So we can formulate this homogenization problem as an inverse problem. So consider, for example, the case of a temperature field that you have observed on the ground. What you're going to try and do is, given a model of your acquisition system, find the candidate that compares best to the data you have observed on the ground. Of course, because your data is noisy, you may not want to enforce strict equality between the predicted measurements and the observed ones, but rather try and minimize a certain comparison function, which will be tailored to the type of noise that you have on your data. So for example, if you have Gaussian noise, you may want to go for the sum of squares, while if you have shot noise, which typically occurs in counting processes, then you may want to go for the more complex Kullback-Leibler divergence. So in practice, it may happen that two candidates explain equally well a given dataset, in which case I propose to use penalization terms. The latter are going to favor solutions which are physically admissible, meaning that they are smooth enough. But we still need to understand where we should seek the candidates. So the traditional approach consists in considering pixelated candidates over certain spherical tessellations. But I find that to be quite unsatisfactory because we know that the underlying field is continuous. There is no reason that it would be tiled as displayed on the left. So what we really want to do is estimate a continuous function, but is that even possible? Because as you know, a continuous function has potentially an infinite number of degrees of freedom, and we only have finitely many measurements in hand. So we are in a bad situation. Hopefully with the penalty term that we have added before, in order to encourage physically admissible functions, we can show using a representative theorem that the solution to this problem are actually finite dimensional and quite well behaved, in the sense that they are a linear combination of very simple basis function called spherical spline. This hence gives us a tool in order to practically recover continuous fields. So let me give you an example with measurements from the Argo fleet. So what you observe on the left are temperature anomalies that have been recorded in January 2011 by the 6,745 Argo floats. And the idea is that we want to recover these temperature fields everywhere in the ocean. And so if we go for the traditional discrete approach, we obtain something like that. So we see that we could fill in the gap, but the problem is that we see strong discretization artifacts. But if you go with the method that I am proposing, you observe that this discretization artifact completely disappear, and you see that you have a much higher resolution and understanding of the underlying phenomenon. In some parts, for example, you see features that were completely lost in the discrete approach. For example, you see it clearly here. In conclusion, I have proposed a spherical approximation framework which is well indicated for the construction of digital twin of the Earth. Indeed, it is compatible with arbitrary measurement types, it is capable of filling in temporal and spatial gaps and hence correcting for acquisition artifacts. It is also capable of correcting for instrumental errors, and its continuous Bayes representation allows for infinite zoom and resampling, which is particularly convenient when trying to combine different datasets together. Finally, it also comes with theoretical guarantees and is very efficient due to sparse and parallel implementation. For the future, I plan on extending this framework to spatiotemporal and vectoral spherical fields. Thank you very much for your attention.